All right, hello pre-calculus. So our next section here is 8.4, and we are going to be talking about systems of nonlinear equations. Now, in systems of equations, right, there's like kind of a elimination or substitution, and generally the same thing is true for the nonlinear equations. You're going to be looking at substitution, and mostly you're going to be using substitution, okay? But whereas I can give you kind of an algorithm, it's like, here's an efficient way of solving these things. I can't really give you one like that for nonlinear because they don't really exist. Okay, it's just kind of a, well, wing it and hope for the best. Okay, so but there are some techniques and there are some things that you should usually try. And quite honestly, these problems are basically coming out of a textbook. And even if they aren't, there's certain classes of nonlinear equations you're going to see on a regular basis, and these techniques are going to be really useful for those. Okay, there's very common shapes that we're going to look at in the next section, okay, with the conics. After that, though, like if you got a bunch of logs or you have a bunch of, you have linear equations with a bunch of logarithms or a bunch of exponential equations that you have to solve, and there's a system of those, like, all I can tell you is, I hope it works out. There's no guarantee that it's going to be easy for this to happen. Okay, there's substitutions you can make to make the process easier, but sometimes these are just a bear, and sometimes you just simply cannot. There's no solving them. Okay, now, well, no analytic way to solve them, and we'll talk about some of those as well. So let's see here. Let's just talk about a couple of examples to start off with here. Okay, well, let me just go over the solution methods. Okay, we have substitution. By far, this is going to be your most employed method. Okay, this is going to be most often. We have elimination. Okay, now elimination doesn't. You're not always going to be able to use this. Okay, sometimes we could be clever and we use it in a way it's like, oh, I didn't think about that. So this is useful, but it's much more rare that you're going to find an elimination problem. Okay, out in the wild. Okay, and then we can always graph it. All right, computers are very good about figuring out the solutions for us on this case, but you should be aware that this is not always available to us, especially like on an exam. You also don't want to have to run to the graphing every time you're going to see this. Like if it's an easy one, you should be able to just to deal with it. But I'd be lying to you if I said that, well, these are easy, because they're not. Okay, so yeah, let's just start looking at a couple of examples here, and we'll see what's going on. All right, so let's see here. We have 4x squared plus y squared is equal to 4. Okay, and then we have an x minus y is equal to -2. All right. So this thing here, this is going to be an ellipse. It looks kind of like a circle, right? There's an x squared plus a y squared, but one side is kind of elongated. And then we have a line, right? X plus y equals -2 is a line. So what we're looking at is some kind of a, how many times does a line go through an ellipse? And just like with linear equations, right? You're not guaranteed a solution. You might get no solution. That happens. The graphs don't touch. We could also end up with, it could hit one time or 2 times or 3 times or a lot of times, or they could be the same graph that's just cast differently. Okay, so there's no like, well, there's only one solution. Like, no, there could be 2 solutions. You don't know. Okay, and again, graphing it goes a long way to like generate a thing, even if it doesn't make a good graph, right? If I have like some kind of an ellipse here, let's see, something like, I'll learn this in a little bit, right? And then x minus 2. So let's see, when y is 0, x is negative 2, right? And when x is 0, y is equal to, oh no, when x is 0, y is equal to 2 up here. And x is equal to negative 2 when y is 0. So we're probably looking at something like that. Okay, so it's possible we're going to get two solutions here. Okay, so I don't think we could possibly get three solutions for a line and an ellipse. I think we're stuck with at most two. But in this case, right, there is, these don't share any terms together. You do not want to start squaring stuff, okay? Because you're going to have to FOIL this out, and we're going to have a middle term, and it's going to get real ugly. Okay, so that is a possibility that we could do, but you really want to save that possibility for, like, we've tried other things, okay? In this case, we want to do substitution, right? If I say, well, this is x is equal to y minus 2, right? Just push this over the other side, right? We have equation 1, we have an equation 2. We still have an equation 2. What we're going to do is we're going to push equation 2 into equation 1, all right? So here we have 4, and then we're going to substitute x. We're going to say, oh, that's y minus 2 squared plus y squared is equal to 4, all right? And then we have an equation that's totally, right, in y. So we have 4, we have y squared minus 4y plus 4, okay, plus y squared is equal to 4. Okay, and then we just have to kind of untangle this and see what we're going to get. So we've got 4y squared minus 16y plus 16 plus y squared minus 4 is equal to 0. Okay. All I'm doing is pushing everything on one side to make it so that we're going to get 5y squared, right, minus 16y plus 12 is equal to 0. Okay. Now, normally at this point, I would ask and say, if only there was some way to solve if only there was some formula to solve this quadratic. But I got this out of a textbook, so I just want to see, like, maybe it factors. So we're going to take 5 times 12 and get 60. And then we're going to look for factors of 16, or factors of 60 rather, that add up to 16. It's 1 and 60, it's 2 and 30, it's 3 and 20. So far, none of those are adding up to 16. 4 and 15, and 6 and 10. Oh, there it is. Okay. So we could go off and say, well, this is 5y squared minus 10y minus 6y plus 12 is equal to 0. Okay. So this is 5y, y minus 2, minus 6. Notice I pulled a minus 6 out, so that changes that sign. Y minus 2 equals 0. Okay. So here we have y minus 2, and then 5y minus 6 equals 0. Right? And then we can just pull this apart, right? Y minus 2 equals 0, 5y minus 6 equals 0. Right? So y is equal to 2, or, right, 5y is equal to 6, or y is equal to 6 over 5. Okay? Now, we're going to take, we have two cases. We're going to take each of these cases, plug it back into what x could be, and those are going to be our solutions. Okay, so in the first case, right, we have the formula, right, y minus 2, that was our substitution. So let's go ahead and like take y equals 2. So x is equal to 2 minus 2. Great, x equals 0. One solution we have, right, is 0, 2. Okay. The other solution, we have x is equal to 6/5 minus 2. This is x is equal to 6 over 5 minus 10 over 5. So 6 minus 10 is negative 4 over 5. So my other solution is negative 4/5, 6/5. All right, and those are the two things that we've got. All right, so just to kind of double check this thing, okay, let's see, I want to do that. I want to do, nope, I don't want to do that. I want to do this one. Desmos, okay? So we can type this stuff into Desmos just to make sure that we're getting the right answer here. Again, this is mostly for a practice thing, but if you're out in the world working, Always good to kind of double check. So, right, 4x squared plus y squared, and that is equal to 4. Okay, so we have an ellipse. I drew it wrong. I messed up. All right, and where is my mouse? There we go. Oh, I know why. My little pen here has a mouse thing on it. If I put it on the pad, it will do that to us. Let's see here. We have x minus y equals -2. Right? And look at that. It gives us the 2 points of intersection, right? -4/5, -6/5. So, that's what we have. Okay, so just to double check it, right? Because I know that typing this into the computer, if you're wrong, you got to redo the whole thing. So this is just a check. Like I said, may not always be available, so we have to be strong enough to do this on our own too. All right. And when we get to 3 dimensions, right, you're not going to have Desmos to help. It's going to be, it's going to be all on you. Okay. Let's see here. All right, you ready for one that's a little bit trickier? All right. So let's see here. We've got an x squared plus y squared is equal to 4. We have a 4x squared plus 9y squared is equal to 36. Right? Now, notice there's an x squared and a y squared. There's an x squared and a y squared. So we could do substitution, right? We could say x squared is equal to a 4 minus y squared, plug it in, and then go with that. However, since we don't have any cross term, we don't have any, we just have x squareds and y squareds, I could multiply this by -4. And we could get -4x squared minus 4y squared is equal to -16. And then put it right underneath 4x squared plus 9y squared is equal to 36. Notice now if I add these together, right, they're going to cancel. We get -4 plus 9. That's going to be 5y squared is equal to 20. Y squared is equal to 4. Right? So we're going to go off and say that y can equal plus or minus 2, but we're going to save this. Y squared is equal to 4. Like, why would you save that? Like, everything's in terms of y squareds. We don't have to go all the way back down to here to know what x is going to be, all right? Because either way, plus or minus 2, we're going to get the same value here. So we're just going to say y squared is equal to 4, okay? So we have x squared plus y squared is 4 is equal to 4. Oh, x squared is equal to 0. So x is equal to plus or minus 0. There is no such thing as plus or minus 0. It's just 0. Okay, we don't have to worry about that. So the 2 solutions we have, right, are 0, 2, and 0, -2. Right? And again, right, we can go check out Desmos and see whether or not we got the good answer. Right? So what are we looking at here? We're looking at x squared plus y squared plus y squared. Oops. Squared is equal to 4, right, the circle. The other one's going to be an ellipse. So we have 4x squared plus 9y squared, 9y squared, right? And that was equal to 36. Right? So notice, excuse me, okay, notice again, right, we get two solutions. We may have gotten no solutions, right? If the circle was entirely inside of the ellipse, we get nothing, right? Or if it was a little bit bigger, we might get 4 solutions. In this case, we got 2. All right, so that's how we work these problems. All right, and in this case, it was set up, and both the ellipse and the circle, those are very common shapes that you're going to find. So even though you're looking at this and saying, well, these techniques aren't going to work for everything, like, yeah, but circles and ellipses are pretty common. So this technique would work for all of those. All right, let's see here. Oh, let's look at the other one, just like it. All right. So let's see here. How about we do x squared plus y squared is equal to 4. Right, so same circle. And instead of an ellipse, we'll do a hyperbola. So we'll say 4x squared minus 9y squared is equal to 36. Right? And then we'll see what happens with this one. Right? So again, right, x squareds and y squareds, we're taking an inventory. We only have x squareds and y squareds. It looks like if I multiply this thing, right, by 9, that this would eliminate. So let's do that. 9x squared plus 9y squared is equal to 36. Okay, then we have 4x squared minus 9y squared is equal to 36. There's often a symmetry with these things, all right? You get 13x squared is equal to 72, right? This eliminated. So we get x squared is equal to 72 over 13. And again, you could brush off and get x is equal to plus or minus 72 over 13. However, let's just go ahead and substitute back in for x squared, okay? Because it's x squared either way, all right? And we could just do that. So I'm going to, pull it back into here. So we have x squared, 72 thirteenths, okay, plus y squared is equal to 4. Okay, so we get y squared is equal to 4 minus 72 thirteenths. So, right, there's 13 cards to a suit and 4 suits to a deck. So I know 4 times 13 is 52. And 52 minus 72 is negative 20 thirteenths, and that's equal to y squared. So we got y squared equals negative 20 thirteenths. You say, wait a minute, y squared should be a positive number. What's going on here? So what's happening here is there is actually no solution because your y's values, these are not real values. Okay, so we end up with a no solution here. All right. So yeah, let's double check it, right, with graphing it and see whether or not this actually works out. But when you tend to get these imaginary solutions, we are trying to plot our solutions on an XY plane, right? We're doing it here. We are not trying to graph them on the imaginary and real plane. I know they look very similar, but the context of what we're doing is very different, okay? So let's go ahead and take a look at what's going on. Let's go ahead and change this to a minus, right? The black one, that's still the circle that we started with. And then the red one, that's called a hyperbola. And you can see, like, there are no points of intersection here. So it would make sense, like, hey, you didn't get a solution. Yeah, we graphed it and checked. So we found out, no, there isn't a solution. We're stuck here. Okay. So let's see here. So, and that could happen, all right? It happens very often. All right. Let me talk to you about one more thing to deal with. This is kind of a neat idea, but it's also infuriating. Okay. Something like, I don't know if you've had trig yet or if you're currently taking trig, but this is called a sign. Okay, it's abbreviated. It's really that number. It's that word. Okay, and all it is, it's the ratio of an opposite over the hypotenuse, the sine of an angle, right? The sine of some angle. This symbol is called theta. And you know how x is like the universal variable for algebra? Theta is the universal variable for trigonometry. Okay, but we might get, sine theta equals theta. Okay, so, wait, the sine of an angle is equal to its angle. Okay, for small angles, that's actually a very common substitution. So in physics, when you have to study pendulums, this is very common. Optics, this is very common that you'll just make this approximation. But if I just wanted to solve this, it's going to be very difficult for me to solve this because the sine, there's, what am I going to, I'm going to inverse it, right? I'm going to undo the sign, and then I'm going to get theta is equal to the inverse sine of theta. Like that didn't help. Okay, I'm still stuck with this horrible equation. And you could look at it this way too, right? We could say x is equal to e to the x. I'm like, okay, well, how do I solve e to the x? We take a natural log of both sides. That didn't help. Okay, there's not a lot I can do with this because I need x outside of the logarithm. But if I take x outside of the logarithm, then I put x in the exponent position. And then I need it in the base position, so I'm back here. So these equations, you can't solve these analytically. By that, I mean, like, there's no algebraic way to do this. Okay, very, very famous one is coming up with that solution. Okay, now there are three. Okay, there's three solutions here. I think 2 is one, 4 is another one. But there's one, right, here's what x squared looks like. And I think it's this way. So you get a solution here and here. But this one, like, that's hard to figure out. Okay, we don't know what that one is. I mean, it's been studied a lot, but there's no analytic way to do this. Numerically, there's a way to get it. Right? You say, well, can I just use Desmos? Like, yeah, but that's not an analytic solution. Okay, it's a numeric solution. So we don't have a way to get this. And there's a whole thing. I'll refer you to number file because it's kind of outside the scope of this class. But you know, you could look at something. These numbers here, e to the x's, log of x's, inverse sines of x's. These are called transcendental numbers. Okay, the solutions to things like x squared, x cubed, x, you know, things like that. Those are called algebraic numbers. They're both irrational, all right, but there is no way to cross the bridge to get one equal to the other, right? There's no analytic way of doing this. So it's really a neat field of mathematics to try to, you know, try to bridge these two. But I think it's been proven that you cannot bridge these. I'm not sure, but there is no nice way to do this. Okay, and some of them we just don't know. I think like e to the pi, I'm like, what is it? Like, I don't know. Is it this or is it this? Well, it could be this. We don't know. Okay, but those are the kinds of questions that you get to ask. Is like, which group does this fit? Like, it's irrational. I'm like, yeah, it's already irrational. We don't have to worry about that. Is it this kind of irrational or that kind of irrational? Okay, and you can't solve them, so you're just stuck with you know, with looking at it. So when you see things like, you know, maybe you have a function of x and you have another g, you have a g of x here and you're trying to equate them, but this one is like an algebraic, it's polynomial, and this one has a log or an e, and it doesn't matter what kind of log, right? It could be this, could be that log, right? Unless it turns out like it's log of like 10,000 or something, unless this reduces to something easy. There is no, you know, there is no looking at this and saying, oh, I can solve that. No, you're stuck. Okay, you have to use a calculator, and that's what we have them for. Okay, so with that, I'm going to stop. I'm going to follow this up with a couple of homework demonstrations and homework walkthroughs so that we can, you know, we can get an idea of what we're doing with that, and hopefully we'll make this section as painless as possible. All right, and we'll see you in the next video. All right, take care.